Okay, so I'll be talking about lower bounds for dynamic distributed task allocation. And this is joint work with Hsin-Hao Su. So in the distributed task allocation problem, we are given a set of tasks and we have a set of agents. And we also have a demand vector, which specifies how many agents each task requires. So for example, the demand vector could be 1, 2, 2. And then our agents have to allocate themselves to the task according to the demand vector. Now this problem has been studied in a variety of different settings. So for example, you could imagine that the agents could be heterogeneous or homogeneous, meaning that the agents could have unique IDs, or the agents could all be the same and they could all be running identical algorithms. Additionally, the agents could be assumed to know the entire demand vector, or maybe just part of it. Also, there's the factor of whether the agents are allowed to communicate with each other, and if so, how. And then there's also the issue of memory. So how much memory do the agents have? How much computational power? And then there's the issue of whether we're in the static or dynamic setting. And in this paper, we're considering specifically the dynamic setting. So what this means is that the demand vector is going to be changing over time. So for example, we could imagine that a unit of demand moves, let's say from task 2 to task 1. So the demand vector is going to change like this. So now we need an additional agent on task 1. And the agents have to reallocate themselves to satisfy the new demand vector. So let's say they do this. So you'll notice that as I go back and forth between these two, actually, even though only one agent needed to move, here, for some reason, they decided to move 2 agents, the blue one and the green one, even though 1 unit of demand moved. And so the goal of this problem is to minimize what we call the switching cost. And this is defined as the number of agents that move if 1 unit of demand moves. So in this case, if those two agents moved in response to 1 unit of demand moving, then and that was the maximum amount that moved over all pairs of demand vectors, where you go from one to the other by moving only 1 unit of demand, then we would say the switching cost is 2. So our goal is to say over all demand vectors, where you go from one to the other by only moving 1 unit of demand, to minimize the number of agents that move. Okay, so our particular version of the problem that we study in this paper was first studied by Su, Doornhouse, and Lynch in 2017. And the particular setting that they studied and that we study is the following. So we're going to assume that our agents are heterogeneous. So they each have unique IDs, although each of them can perform any of the tasks. So they don't differ in ability, they differ in the fact that they each have a unique ID. Additionally, for these other 3 settings, we have the following. So we are going to assume that the agents know the demand vector. So the agents can observe the demand vector, the complete demand vector. And we're also going to assume that the agents are not allowed to communicate with each other at all. And they also have no memory at all. And these restrictions, what they amount to is that we end up studying kind of the combinatorial aspects of this problem. And that will become clear when we define the actual problem statement. So more formally, here's what the problem statement is. So what our goal is now is to define a deterministic function for every agent. So we're going to have 1 function for every agent. And our goal, again, is to minimize the switching cost, which is the number of agents that move if only one unit of demand moves. So each agent has its own function here. As you can see, all 5 of the agents have functions respectively F1 through F5. And these functions take as input the demand vector. And as output, they produce what task that agent is working on. So as you can, this is consistent with the list of settings here because each agent has its own particular function, so they're heterogeneous in that sense. The agents know the demand vector because they're allowed to take in the demand vector as input to their function. However, they're not allowed to take in any other information. So they're not allowed to take in any information that they stored in memory or communication. They can only take as input the current demand vector, and based upon that information, they have to decide what task to do. Okay, so that is the problem statement that we're studying. And I'm gonna come back and give some more intuition about what this problem statement is actually saying, because I think at first it's a difficult one to wrap your head around. So, but first I want to just take a quick detour and say a couple of reasons why you might care about such a problem. So initially this problem was studied in this paper from 2017, and it was actually initially formulated in the context of collective insect behavior. So you can imagine that each agent is an ant, and in the ant colony you need to do a particular set of tasks, which may change over time. So this was the setting that it was originally introduced in. And as you can see from the statement, the statement certainly doesn't closely represent what ants are actually doing. However, studying this problem statement may give some understanding of the combinatorial aspects of what's going on with distributed systems that arise in biology or human-made distributed systems. Another interesting thing is that this problem turns out to be have a relationship to metric embedding problems. So it turns out, I won't go into the details, but this problem statement can actually be reformulated as a problem of getting a low distortion embedding in Hamming space. And thirdly, I think that this is a nice natural combinatorial problem. And the purpose of this talk is to familiarize you with the problem and maybe get you interested in this problem, because there are, the problem is far from closed. There are a number of open problems in this area, and there's a gap between upper and lower bounds. Okay, so let's return back to the problem statement. And what I first want to show you to give a sense of this problem is an upper bound on the switching cost of the number of tasks minus 1. So that is to say, we're going to show that there do exist a set of functions, F1 through Fn, so that if one unit of demand moves, if starting with any demand vector, if one unit of demand moves, then at most, the number of tasks minus 1 agents move. So in this case, at most 4 agents move. So again, recall that each of these agents has its own individual function, and each of these functions takes as input the demand vector and has to output what the task that agent is working on is. So here's what the definition of the functions is that achieves this switching cost. And this upper bound was observed, it's a simple upper bound that was observed in the original paper that studied this problem. So the definition of the functions is simply to fill the tasks in order. So what that means is that you look at the demand vector and you look through the tasks in order, task 1, task 2, task 3, and you just place the agents in order based on the demands, agent 1, agent 2, agent 3, until you get to the end. So here, for example, task 1 has no demand, task 2 has 1 demand, and since we're filling things in order, we put agent 1 there, etc. Okay, and it's important to note that this function, this set of functions can indeed be computed by each individual agent just given the demand vector. The reason for this being simply, let's say I'm agent 4, I would just look at the demand vector and see where the tasks, the demands sum to, where the prefix of the demands sum to 4, and then I would put myself at that task. Okay, so why does this achieve switching cost number of tasks minus 1? So if you think about it, the worst thing that can happen here to get the most agents to move is that a unit of demand gets moved from task 5 all the way to task 1. So let's imagine that happens. So we just moved a unit of demand from task 5 to task 1. Now, what is the new allocation going to be? Well, we're again going to be filling the agents in order. So, but this time, task 1 has 1 unit of demand, so our agent number 1 has to go into task 1. And similarly, agent number 2 has to go into task 2. So what's going to happen is that they're all going to shift over by 1. And more generally, the number of agents that shift over by 1 is just going to be the number of tasks minus 1 at most. So this shows that there do indeed exist a set of functions that achieve switching cost number of tasks minus 1. And the question is, can you do better than this? Okay, so what I want to show you next to continue giving you a sense of this problem is a simple lower bound that was also observed by the initial paper that studied this problem. And this is a lower bound saying that you cannot achieve switching cost 2. You cannot achieve switching cost 1. So the lower bound is that it's at least 2. So what this means is that we're going to be showing that there do not exist a set of functions so that if 1 unit of demand moves, only 1 agent moves, even if your number of agents is only 2 and your number of tasks is only 3. So the way that we're going to show this is first by recalling the requirement that we have, which is that any demand vector has the same allocation of agents regardless of how the demand has moved around in the past. And that is because each agent just takes as input the demand vector. So they have to make their decision solely based on the demand vector. So if you have a particular demand vector at one point in time and at another point in time, then the allocation of agents at both of these times has to be the same. Okay, so in order to show this lower bound that you can't achieve switching cost 1, what we're going to do is just assume for contradiction that there do exist a pair of functions, F1, F2, that achieve switching cost 1. And then we're going to start with a demand vector and move around some demand, and then eventually reach this initial demand vector again. But it will have a different allocation of agents, and that will be a contradiction due to the requirement that any demand vector has to have the same allocation of agents regardless of when this happens. Okay, so the proof of this fits on one slide. If I just make this picture smaller. So let's imagine that this is our initial demand vector, 1, 1, 0. And we have these 2 agents allocated to these 2 tasks. Now, let's suppose we move a unit of demand from task 2 to task 3. Now, our only choice of which of which agent to move is going to be to move the red one from task 2 to task 3, just because we're assuming that our switching cost is 1. So we're moving 1 unit of demand and we have to move only 1 agent. Our only choice is to move the red one. So this is going to be our allocation. And then we're going to do this again. We're going to move a unit of demand from task 1 to task 2. And this time, the blue one has to move. That's the only choice. And now to finish this off, we're going to move a unit of demand from task 3 back to task 1 to get ourselves to the original demand vector. And the agent that has to move is the red one. And so we have this allocation of agents, which is different than our initial allocation, even though the two demand vectors are the same. So this is a contradiction and shows that you cannot achieve switching cost just 1. It has to be at least 2. Okay, so this is these are the upper, sort of simple upper and lower bounds observed by the initial paper on this problem. And that initial paper also has one more result, which says that, okay, we know that you can't achieve switching cost 1, but can you achieve switching cost 2? And what they show is that indeed you can achieve switching cost 2 if your number of tasks is at most 4 and your number of agents is at most 6. And the proof of that is this picture. So what they do is they actually just list out exhaustively all 84 demand vectors and all of the allocations of agents, and you can go through and check that indeed the switching cost is 2. Of course, this proof method is not very scalable since the number of demand vectors increases very quickly as the number of tasks and the number of agents go up. So you might imagine that that you could still achieve switching costs 2 with larger numbers of tasks and agents, but we just didn't see how to do it using this brute force method. However, our first result says that actually this result is tight in the sense that if you just have one more task, then you cannot achieve switching cost 2. Okay, so our first result says that their construction is tight, meaning that switching cost 2 is impossible if your number of tasks is at least 5 and your number of agents is at least 3. So we're going to use n as number of agents and k as number of tasks. Okay, so now the question is, can you achieve switching cost 3? And our second result in this paper says that there are certain situations where you cannot achieve switching cost 3. So that is to say there exists some n and k such that switching cost 3 is impossible. In this lower bound, in this example, the number of tasks is absolutely huge. It's like a tower of height n. But it does show that there exists some n and k such that you can't achieve switching cost 3. Okay, so these are the results in this paper. And although what we would really like to show in this problem is a super constant lower bound. These lower bounds are just saying you can't achieve switching cost 2 or 3, but you would imagine that the switching cost increases, at least at some rate, with the number of agents and the number of tasks. And another question is whether you can achieve a better upper bound than just the easy upper bound that you saw earlier of shifting all the agents over. So there's actually some follow-up work that answers these questions. And the follow-up work shows that indeed you can get a super constant lower bound. You can get a lower bound of log star of k, number of tasks. So that this kind of extends this theorem 2 here, saying that the theorem 2 here had said that you can't achieve switching cost 3 if you have a very large number of tasks. And here we say, okay, you can't achieve switching cost n if the number of tasks is huge. And then secondly, the follow-up work shows that you can actually get an upper bound of polylog and NK. So this algorithm you saw before of everything shifting over and you get switching cost number of tasks, it turns out to be far from optimal, and you can actually get polylog. But there is still a large gap between the upper and lower bounds, of course. And that would be really interesting to find out what the true answer is. That's all. Thank you.